Module 4, Investigation 3, 1 unit growth and decay factors, percent change, and initial values. For exercises number 1 through 2, determine the growth or decay factor, percent change, and initial value for each of the following exponential functions. Number 1, f of x equals 34, 1.19 raised to the x. Refer back to Module 4 Investigation 2. We had this chart. If we take a look at this, the structure of an exponential function is of the form f of x equals a times bx, where a represents the initial value, b represents the growth or decay factor. So just with that information right there, we can see that our 1 unit growth factor is 1.19. Our initial value is 34, which just leaves the percent change. So here we have some information about exponential growth versus exponential decay, and then the percent change, we have this nifty little paragraph here. It is helpful to describe an exponential function based on the percent of increase or decrease. For example, the statement the number of homes purchased increased by 2% each month represents a situation that is exponential due to the repeated increase for each month. In this situation, percent change is 2% and the growth factor is 1.02. Each month's number of houses sold is 102% of the number of houses sold the previous month. If the statement changed to the number of new homes purchased decreased by 2% each month, then the percent change is negative 2% and the growth factor is 0.98. Since this factor is less than 1, we sometimes call this a decay factor. In general, exponential functions have a growth or decay factor of b equals 1 plus r, where r represents the percent change. Remember that r can be negative. Something that's interesting to note here is that if b is 1 plus r, then b minus 1 equals r. So that percent change, we can always find it by taking our growth factor b and subtracting 1. And number 1, I can look at this one and see that the percent change is positive 19%. And that's an increase. We could always say, okay, what's our growth factor? It's 1.19, so if we take 1.19 and subtract 1, we get 0.19, which is 19%. And that's an increase, of course. So for number 2, g of p is 1.578 times 0.68 raised to the p. Our initial value is 1.578. Notice this is the place where if we put p equals 0 here, 0.68 raised to the 0 power is 1, so we just get our initial value 1.578. The 1 unit decay factor is 0.68, and to find the percent change we just need 1 minus 0.68. I'm sorry, we really need 0.68 minus 1, because we're going to get a negative value here, and that's going to tell us that it's a decrease. And 0.68 minus 1 is negative 0.32, or negative 32%. Or you could say a 32% decrease. In exercises number 3 through 4, determine the growth or decay factor, percent change, initial value, and function for each of the following tables modeled by exponential functions. So for number 3, we have these x values for our inputs, and the f of x values are the outputs. I can see right away that the initial value is 16 because that's when x is 0. I also noticed that there's a decay. The output is decreasing. And notice what we're decreasing by. We're decreasing by a fourth each time. 16 times a fourth is 4, 4 times a fourth is 1, 1 times a fourth is 0.25. So that tells me that the decay factor is 1/4. You may notice that we have every piece that we need to write a formula, because recall that when we have, let's see, the formula f of x equals a times b to the x, a is the initial value and b represents the growth or decay factor. Since we've already identified the decay factor and the initial value, we know what our function will be. And it will be f of x equals the initial value, which was 16, times our growth factor, 0.25, to the x. Now we also could find our 1 unit percent change. Notice that if the decay factor is 25%, then the percent change will be 75%. We could do it like this. 0.25 minus 1 is negative 0.75, or negative 75%. Or we could say that there is a 75% decrease. Number 4, the let's see, I don't have 0 in my table, so I don't know the initial value. How can I find the growth factor? It's not as obvious as the previous one, where I noticed where we were multiplying by 1/4 each time to get the new value. In this one, what do I multiply 260 by to get 299? Well, just asking that question, it's pretty clear what we need to do to solve for the growth factor. We just need 260 times something. Let's just call it G for growth factor, will equal 299. Just like in the previous problem, 16 times a fourth gave us 4. To find the growth factor, we just need to figure out what do we need to multiply 260 by to get 299. This is just a division problem. G will be 299 divided by 260. And our answer is 1.15. Okay, now we can see the percent change. We're going to be increasing by 15% every year. You could say 1.15 minus 1 and get 0.15, but it's pretty clear here that this is a 15% increase. Okay, so we're still missing the initial value and our function. So how can we get our initial value? The way I'm thinking about it is, imagine that 0 was over here in my table, and what would I need? What would the number be right here is what we're looking for that initial value. Let's just call that initial value A. And to me, here's the really interesting part. Since we know the growth factor, we can figure out what A is. We know that if we took A and we multiplied it by the growth factor of 1.15, we're going to wind up with 260. So A is simply 260 divided by 1.15. That's pretty close to 226. It's 226.087 to be exact. Now that we know our initial value, we can easily write the function. So the function for exponential growth, we start with our initial value, 226.087, and we have our growth factor raised to x. In exercises numbers 5 through 7, determine the growth or decay factor, percent change, initial value, and function formula for the exponential function with the given graph. So right away, I notice a few things here. The initial value looks to be about 30. That's where we cross the y-axis, the y-intercept, when the value of x is 0. Let's see what else. Notice that it's an increasing function, so we're going to have a growth factor. Let's see. That's about it for now. Notice we do have a couple of points here, 142 and 258.8 and 382.32. So just like in the last problem, we can find the growth factor because we take these numbers here and we multiply them by the 1 unit growth factor to find the new value exactly 1 unit later. So we could say 42 times g equals 58.8, or g is equal to 58.8 divided by 42. And we get 1.4, our growth factor. Now I can see that the percent change is 40% increase. I could just look here and see that there is a 0.4, that's 40%. You could also just say the growth factor minus 1 and get 0.4, which is 40%. Alright, now we know our function is equal to, it's always f of x equals the initial value times the growth factor raised to x, or in this case, let's see, we have the initial value is 30, the growth factor is 1.4, and our input x. Number 6. Here we have a decreasing function, so we're going to be looking for a decay factor this time. It looks like our initial value is 50. And we need to find the 1 unit growth factor. So notice we have these 2 points, 1 and 40. And then 1 unit away from 1 is 2, and then we have the corresponding output of 32. We also have this point, but we can find the growth factor just with these. We know 40 times the growth factor will equal 32. So the growth factor equals 32 divided by 40. And I apologize for saying growth factor. This is a decay factor. You can tell because it's smaller than 1. So our decay factor is 0.8. And that tells me that we have a 20% decrease is the percent change. Again, just the 0.8 minus 1 is negative 0.2, or negative 20%. Now we can easily find our function. It's just the initial value of 50 and the decay factor raised to the power x. Okay, this one looks like it might be a little bit trickier. I'm not sure about that initial value. It looks like 3750 or something. Not sure. I know that this one's a growth function because the function's increasing. You can see that as x increases, the y values also increase. We do have 2 points. We can get started taking a look at those. Negative 2 and 25, then negative 1 and 30. So what do I multiply 25 by to get 30? That's going to be the growth factor. 25 times the growth factor will give us 30. So the growth factor is that final value divided by the initial value. And we get 1.2. The percent change is 20%. Simply 1.2 minus 1. Now, how are we going to find the initial value? We know that our function would look something like this. But we don't know our initial value. We do have a point that is 1 unit away from 0. So if we wanted to find 0, like the output that goes with it, we can simply multiply 30 by our growth factor, by 1.2. And we get 36. So that must be our initial value, which means our function is 36 1.2 x. In exercises 8 and 9, determine the growth or decay factor, percent change, initial value, and function for each exponential situation. Number 8. An investment of $3,300 increases by 4.7% each month. Okay, if we're increasing by 4.7% each month, the percent change is 4.7%. That's the 1 month percent change. The growth factor, I know, is simply going to be, well, 0.47 is the same as 0.047. I know my growth factor is going to be 1.047. You may remember from that box in Module 3, or investigation, the growth factor is B equals 1 plus R, where R represents the percent change. So, that's sort of how I did it here, but yeah, 1.047. Let's take a look at the initial value. Not sure about the initial value. Let's see. Oh, an investment of $3,300. So there's our initial value. So our function f of x equals $3,300, 1.047 raised to x. Number 9, after having 1.4 million people in 2010, the population of a town has been decreasing by 2.1% per year. So 2.1% decrease is the percent change, or negative 2.1%, which is negative 0.021. Now my decay factor, I'm going to use this time. It's 1 plus the negative 0.021. The decay factor is 1 plus the percent change. So 1 minus 0.021 is 0.979. 1.4 million people in 2010, so we could call that our initial value, 1.4. We'll just understand that that's million, and then our function, we could say f of x equals 1.4, 0.979 x, and here it might be important to give some context. X is the number of years since 2010, and our output f of x will be the number of people in millions.